I'm Bhavadhir V. Bharadwaj. Welcome to episode 13 of Genesis of Tomorrow. The following is a conversation about quantum mechanics, geometric algebra supercomputing, the GASC, non-conformity in science, and much more with Dr. Alexander SOiGUINE, an independent researcher and the founder of SOiGUINE Supercomputing. Also, folks, 86.1% of you watching this have not subscribed yet. So, if you're able to derive even the slightest bit of value from the show, please support us by clicking that subscribe button so that we can keep improving the quality of the episodes and keep on bringing such wonderful guests over for you. And now, without any further ado, let's get right into it. Enjoy and thank you. Yes, we are rolling now. Okay, so I
Okay.
do have an outline of the basic topics that I would want to talk to you about. However, during any point in the conversation, you feel like that you want to maybe go on some tangent and talk about any tangential topics, we can do it. I want this to be a conversation more than an interview. So, feel free to go and talk about other subject matters that you might find relevant.
Okay, I think everything will go successfully. So thank you.
Right. Okay. First and the foremost, we have to start with this, right? Uh, Before coming across your LinkedIn profile and reading about your work a little, I was not familiar with the geometric algebraic supercomputing approach, this framework of yours. And you say that the main project of your company, of your research institute, is the Project Geometric Algebra Supercomputing Initiative, the GASCI, which pursues the idea that a really valuable and productive mathematical model, particularly applicable to quantum processes, can only appear when formalized in constant adequate terms. First of all, what is this geometric algebra supercomputing for the absolute unfamiliar and novice?
Okay, I understand. It's not your fault, but it's very it's very novel approach. Maybe you heard that the basis of quantum computing is entanglement of qubits. Did you hear about that? Do you
Yes,
mention what is
yes.
qubit?
Uh, my understanding with qubits is that because I come from a computational background, right? Computer science, artificial intelligence. So my understanding of qubits was that what bits are for classical computers, qubits are the equivalent for quantum computers. And they utilize quantum phenomena to carry forth computational processes.
Yes, something like that. But the long history began from generalizing of complex numbers to objects of geometric algebra. So in geometric algebra, I called elements, basic elements, as G qubits. G qubit is uh, you can imagine that's direct sum of scalar plus b vector, and b vector is imagine as a disk in three-dimensional space. So it's generalization of complex numbers instead of formal, say, alpha plus I beta. Now it is alpha plus beta and unit element in b vector in three dimension. That's the beginning of the story. And based on that, the lift, so to say, lift of qubits appeared instead of qubits, G qubits as such elements of even subalgebra of geometric algebra in G3. So it is generalization of complex numbers, and the whole story about quantum phenomena changed substantially. And this structure allows to create calculations generalizing, making something absolutely novel compared to regular, commonly accepted quantum computing, which is based on entanglement, when assuming that one state, when changed immediately through entanglement, other states change simultaneously. That's the general idea
Uh,
of quantum computing. In
hmm.
my approach, in my approach, everything is not going in Hilbert space, but everything is going on three-dimensional sphere, because G qubit can be mapped directly back and forth on three-dimensional sphere, four numbers, which is scale apart, and three components of B vector parts. So everything is going on three-dimensional sphere, S3, so to say, and all that allows everything to go absolutely very different, I would say. And I created simulation schemes based on special solutions of Maxwell equations in that geometric algebra terms, and there appear algorithms which can be simulated directly on GPU-based computers. Not, I prefer not to work with NVIDIA cards, but with something more. Uh, do you know what is NVIDIA cards?
Yeah, yeah. Jensen
Okay,
Hyong
but
has been going pretty wild right now.
great, that's great.
Hmm.
And I prefer to work with something available, for example, from Qualcomm, where graphics unit is part of motherboard. It is much more uh, convenient. Instead of using NVIDIA cards, which are, so to say, external devices uh, to motherboard, this is the chip contains uh, contains graphics card inside itself. And also, I prefer to do all that in Linux distro. I work mainly on Ubuntu. It's the more accepted. It's not critical, but Ubuntu is easier to get, to support, and all that.
Okay, I really think that okay, you know what? I'll get onto this maybe in a little while, but before that, I feel for people to be able to better fathom the idea about this entire framework that you have curated with such extensively intensive research, I feel it would be really viable for them to get to know about your background in general, not only particularly related to your education, but more so related to your motivation and your journey of how you realize that, right, there might be certain limitations with the current understanding of quantum framework and how it's applied to quantum computing, and there are aspects which I have ideas about which can enhance the entire quantum understanding and take it to a whole new level. So just probably taking us through that entire journey, what has it been like over years?
So this journey began many years ago, when I realized that complex numbers should be generalized. I am a mathematical physicist in my background, it was my first work article, scientific article on that. It appeared more than 20 years ago, and it was published in a book. And after that, after many years, I decided to return to that. And so I created this novel generalization of complex numbers as, as elements of even subalgebra or of geometrical algebra G3. And based on that, I wrote a lot of things explaining how all that going, how it can be applied to basic things of quantum mechanics, and how it can be lifted from qubits to more general object. So if you imagine, and everybody knows that you can imagine geometrically qubits as some vectors running in some formal plane around unit circle. But G qubits, my generalization, it is unit vectors, but they run not along circle, but they run along sphere. That's geometrically my idea. Uh, all that allows to to reformulate many things mysterious in a kind of quantum mechanics. I wrote about that as double slit experiment, for example, one of the basis things in quantum mechanics, or model of hydrogen atom, also one of the basic things in quantum mechanics. So everything appeared to be in this approach very convenient and feasible, I would say. And that's one side. But another side, more important, that we can follow that and to create effective simulation of computing that is superiors can be to entanglement based quantum computing, which is accepted by 99.9% of people, who, when you say that what is quantum computing, oh, it's entanglement between qubits. But now it's very different, and the 99.9% of people say, well, what the hell is that? We work differently. Yes, billions were invested in that research. They are trying to create entangled qubits in different ways. Such as giants as Microsoft, Intel, Google work on them. They spent huge amount of money, but no final success yet. I want to create simulation software which is much cheaper and faster and easier to be understood. That's why I'm trying to. My idea is to collect money. Maybe some crazy people decide to invest in that.
I really feel okay. This was the point that I was actually wanting to come to. I really feel novelty and non-conformity are two things in science that has had the one of the, if not the greatest, contributions at pushing our understanding and the perception of reality that we harbor over the course of history. When you go back to Galileo's time, and there was this geocentric theory, he was the first person to say, all right, we might not be at the center of the solar system. And he was of that 0.1% of people who suggested that. But that non-conformist idea, or that uh, ability to probably look at the generally perceived and accepted belief and be able to say that this might not be the most viable option, this explanation might really be better explanatory for the reality as it is, that is really crucial. What is your opinion upon this role of non-conformity in science and technology and advancement in general of humankind?
My belief is that what I'm trying to fully implement in terms of geometric algebra, that it is so feasible and straightforward that it will be much much better than generally accepted approach to quantum computing. It will be absolutely not so expensive. It will be easy to be simulated on regular computers, and it is different thing. And it resolves huge amount of problems which are today connected with quantum computing. All this crazy hardware, what they are doing at temperatures close to zero temperature, and it is. And I'm writing software. I have some preliminary variants of software written in OpenCL, because OpenCL only works with graphics unit, not NVIDIA graphics unit, which are sitting on motherboards. And I have something written already, and I'm trying. I need just interface, finish interface to make it more convenient for people. But all that is, how to say, realizable, and I will do I will do what is what people in conventional quantum computing are trying to do. I will do it myself, one person, and the simulating software will run uh, with superiority in, in the results compared to quantum computing. At least not less, much better actually.
With this traditional, so to speak, conception of quantum computing and its hardware aspect, there are challenges of environment, may it be the environment noises, decoherence, fidelity
Yes.
issues. What what benefits or ease does this approach provide when we look from a very hardware perspective of things implementing this?
Yes, you're right. The main problem with quantum computing, as it's the people are trying to implement today, is when they create even system with amount, sufficiently large amount of qubits, but this noise reduction to noise is the main problem, and it is related to all that is running on hardware level, because all that hardware, all that physical hardware systems, they need to reduce to eliminate noise. You are right, but it's not happening in my approach, since we do not need that crazy hardware. Everything can run on simulating uh, software. That is the story about reducing noise. It just disappears, and that's a new life, much better life.
I mean, really, the greatest challenges that we face right now at realizing the complete potential of quantum computers, this approach really seems to just take all of it out of the picture. Like, suddenly you have to worry about none of it and just focus upon the ways in which you can better implement and apply the effects of quantum mechanics through quantum computing.
Yes, you're right. It would be nice. It would be nice to practically uh, write variant of my approach to some particular problem, which people are trying to do with quantum regular convenient quantum computers. It is a great idea. That's what I'm thinking about. I need to select something from the area to get some particular example of what is good proof of good quality of quantum computing, and I need to do from my side and to compare it and to demonstrate that my approach is much easier without eliminating all problems of conventional quantum computing. There is another side of all that story because, on, on one hand, 99% of people do not know about my approach and do not believe it in it. I would say it is good because when people begin to realize what I suggest, they will immediately want to kill me. You understand? So my approach of my company, when it becomes a little successful, will be, what is this competition in
Having
on Mars?
large target on your back, right? I mean,
Yeah,
talk to me about this a little more. Uh, how, to what extent does this business side of science and technology, does that affect the propagation or the outreach of novel approaches which are maybe not mainstream? Like, how
yeah,
do
yeah,
these, yeah,
yes. You are right. What I'm suggesting, it's not in mainstream. It's something very unusual for people. But when more and more people begin to realize that it may be huge successful in the nearest future, then then I become in very dangerous situation. You know what I'm talking about. But I want to continue struggling.
that that is aspirational, to say the least, for anybody who is, personally, for a young person like me, right? Because I am doing my undergraduate right now, so it's just like I've just entered my higher education, that's fear. For somebody like me, talking to you who has got this indomitable belief in his work of scientific pursuit that he's been dedicating himself to, that really is something that I'm inspired by, and I'd look forward to imbibing that in me. And I think that would hold true for anybody who's young and maybe watching this. And if anything at all, I would really like them to take this away from this entire conversation. But what I want to ask you about this, why I took this thought trail, is what do you think is the role that the young people or the youth could play in propagating your work? Because with the advent of social media and outreach, it could be very viable for such novel theories and approaches like your work to maybe not get mainstream in a way, in a traditional sense, like how IBM's or Microsoft's work gets that attention. But through social media, it might really reach out to people in a way that gets prevalent over time through that snowball effect.
Yes, you are right. You are right. It's better to deal with young people who are brave enough, I would say, brave enough to be out of mainstream. And in several years, they will be part of something, some absolutely new, huge business area that will they will grow from something zero to something huge and highly successful.
Dr. Alexander, tell me more about this entire framework of yours. If we take a more theoretical approach, how would you define its origin, its genesis? How were you able to build it one block at a time from its conception to where it is now? How did you kept on improving it in a very theoretical and mathematical kind of way?
You know, what I do have right now is that, so to say, theoretical side is solid and more or less finished. I need to work on this simulation software on graphics card. That's the main job I will do. I cannot do everything myself. So I do a lot of, but if I have a couple of students or young scientists who can do good programming in OpenCL, first of all, in some or another kind of Linux distros. Then, with the help of them, interface convenient implementation will be done, and that is something that can be put on market. That's the first step, and that's the first phase. And in this situation, with the help of a couple of young people, uh, so good in programming, that's the first phase. And after that, we are becoming something dangerous for big fishes, like like Intel or Google or whatever. You know, even today, with my very modest uh, level, so to say, yes, phase of developing, I begin to receiving suggestions. We want to acquire you. Can you imagine? Okay, that's another side of all that market story.
But okay, talk to me about this itself. Like, what do you think are the most viable commercial applications of quantum computing and by extension of your approach to it? What would be the first plausible application that you think you might be able to materialize through your framework?
You know, you can look at what specialists are writing about what is good side of where quantum computing is applicable, and all that is covered with my approach. All of that, but there are new things that are not covered by conventional quantum computing. Uh, for example, in blockchain schemes, I can rewrite contents of blocks of information in blockchains back in time. Can you imagine that? It is something very dangerous for blockchain schemes. And is one of my superiorities compared with conventional quantum computing, because nobody at least say anything about that. But I directly see how can I do that.
Wow. Okay. Uh, to simplify it for those who do not have an idea about how significant that is, please give a breakdown of how you are able to do that with your framework.
If I continue speaking about that writing back in time, all that simulation things with special kind of states in my sense, it is the very notion of what is future and what is past disappears, by the way, because in the computer simulation schemes that follow from my approach, when you change something uh, in in states, they immediately change forth and backward in time.
Okay, explain it. I might be sounding really dumb right now, but I'm really
You know
interested in that.
what is the reason, what is the effect? And in this, when this my scheme is implemented, then reason and effect, um, it becomes not not different at all. Everything happens simultaneously, so to say, backward and forward in time and through the whole space. By the way, it is amazing, but
It
the
is. It is.
particular case of that is that I can, in blockchains, I can write back and changing records back in time.
If you This is a very, how do you say, the first step implementation and implication of your research, and it's this property of its. But extending it in the long term, what is the most far-fetched, even to say the most sci-fi like ability that this particular property of your framework will be able to perform? Because I feel that the way it's able to completely nullify the sense of a past and a future and able to perform everything without any regard to the causation and effect is am I right? It's able to disregard that, right?
Yes, you're right. It is such be- fantastic, maybe, area of implementation. So from my schemes, and it's necessary to think about that. It may be dangerous, but it should be developed. If it's available from my approach, then we'll try to do something. We'll try to change something in past.
I mean, that's right, and it is dangerous in conception, but I really feel the best way to prevent misuse of any scientific conceptualization is to know everything about it. Would you agree upon that? Like, we know everything there is to know about it, and then we just make it known to the world. That way, there is accountability and deterrence with regard to that.
Yes, you're right. It is such a side of all of the things which follow from my approach. It may be dangerous, and it should be thought about. Maybe not to do that at all.
Maybe taking a little detour here, how do you think science in general and the with it the understanding our understanding of life and existence at large has evolved over time?
Mm, what ca- what can I say? The idea that if we can, at least on computer simulation side, if we are able to simulate changes back in time, back in time. Uh, then it is very dangerous side of all that. But we need to think of all that. But if it's not just it's not just computer simulation. It can be implemented on real physical level, because if we create some kind of, say, photonics features to for such channels, when we can where we can to distribute the signals, so to say, back in time. It will be something crazy interesting and dangerous.
I bet. Okay, what would be your advice for people, aspiring scientists, or people who are beginning to get into the field of scientific research and development?
As I wrote many times, is that all that is for brave young people, for brave young people, because they shouldn't. If they need to be not afraid to be out of mainstream. If they want to create some wonderful, crazy, I would say, future, they can participate in that. It's not about to get advances and getting job at Intel or Google or whatever. It's something very different. Young people should be a little crazy about about life.
And I mean, yes, yes, yeah, it's I agree to it. Also, I feel that umpteen times scientific curiosity is traded by people to garnering more material or societal, fitting in to the societal expectations of material success. Would you agree with that?
Yes, I agree to that. The most of people, they want to be taught in mathematics and physics, to get good job. That's the most of people want. But this is not immediate about getting good job. It's just to participate in something of developing very new future.
Um. Okay. Before I jump into the towards the conclusion of this episode, there is something that I would again want to talk to you about. How long do you think, in terms of the timeline, sort of? Uh, okay, two parts. Firstly, how long do you think this framework of yours, that the simulating bit that you're working on, would be able to materialize? How long will it take for it to fully develop, for you to be like, okay, right now this can hit the
From,
market?
from my previous experience, is I fully believe that with with the help I talked about, so some assistance of programmers and with some financial assistance, the first phase will be done in not more than 1 year, and then further development of going into market, it's maybe 2 3 years after that, later. So I'm sure that if we are successful, if we are not swallowed by big fishes, then in 5 years we will become billion value company.
Wow. Okay. um the second part of the question is that, if you are comfortable to talk about it, how do you think your childhood inclinations or your childhood influenced your scientific curiosity and your ability to be able to set yourself apart from the crowd, think for yourself, and have that element of bravery, as you mentioned?
You know, when I was teenager, and when I first got known something about quantum mechanics, I decided that It's something to live for. And as of today, I am very close to doing something what I thought about years and years ago. So I think that if I am successful to put all that in solid reality, all the results of implementation of my approach, then it means that my life was successful.
Wow. Towards the culmination of the show, there's this segment that we do. Dr. Alexander, what is your word to humanity at large?
Be wise and be brave.
No
And
truer word said. I mean, yes, especially the bravery part. It would really be good to have such, again, as I said, non-conformist way of thinking be cultivated in people who are pursuing scientific careers and be able to develop and curate and think for themselves and not be afraid to pursue a line of research or scientific thinking that they feel is different from the mainstream and work towards making that mainstream.
yes, the most of people, what they're thinking about. Do they have enough money to buy food, to buy gas, to have a car, to build a house? That's the common thoughts of most of people. But there are some amount of people, I believe, which are looking wider on everything, and they understand that there are things maybe more important than building a house.
Okay, this is one thing that just suddenly uh, came up in my head. Uh, what do you think the geopolitical scenarios and the geographical demographic plays in the conception and the realization and the pursuit of research and development?
Uh, I do not consider myself as a big specialist in such things you are talking right now, but it's difficult for me to be a judge in such things because if we look around the world, what's going today, many things looks not good, I would say, and I do not pretend to state that my software simulation life can substantially improve for that, but it is something that will help to some extent.
Dr. Alexander Soigwin, thank you so very much for being on the show. It was a pleasure and an honor talking to you.
Yes, it was. All pleasure was mine. I'm very thankful that you connected with me and talked with me. Maybe you'll get some ideas.
Definitely, definitely.